And so is there any problem about sharing?
Oh, sorry, let me see. Can you see that?
Yep.
Okay. So I did some settings from the previous and I've tried and I think it's working.
Have you uploaded your data? Downloaded?
Yes.
Okay.
Let's see.
It may be deleted because when you close your browser and reopen it, you have to upload it back again. Great. How many options or how many different layouts have you tried for this?
Just the previews on the website. I think yeah, there are 4 human and 1 garden and those options. I tried 3 of them, I think.
Okay, do you have all the output data for the needed volumes and the number of photovoltaic panels? Because we will be needing for the Grasshopper part for today.
I only download 2 of them.
Okay.
Do I need to download them all right now?
No worries. Just try to note down the different outputs for different layouts.
Okay.
So that we can try different options in Grasshopper. It would be more playful when you have a lot of different inputs.
Sure.
But it's better to test it all out in Grasshopper.
Do I need to download the plugin on the Grasshopper or?
Yeah, we will share the Grasshopper code today. But first we will go over it like yesterday. We will
sure.
explain how it works, and then we will upload and test it out together.
Okay. So I'll stop sharing my screen.
Okay. Great.
Okay.
So maybe in the meanwhile, you can try another kind of scenario, Sofia. What do you think about it? Okay, then. How about you, Yasemin? How is it going on?
Hello. I tried some scenario, so I can share my screen.
Of course.
Okay.
Can you see my screen now?
We cannot see right now. If you can click on the share screen button at the bottom right, we can see it. We can see now.
I examined some scenarios and I tried to note down different parts of that. As an example, it's for one astronaut and 20 days. And these are diagrams related to that. And another one, for example, 2 astronauts, 30 days. And 4 astronauts, 19 days. And some other different scenarios. And here is the final result of different scenarios.
It's great. So maybe you can add them for the number of photovoltaics for these scenarios, because we will also editing these numbers of the photovoltaics in the Rhino. It's very nice to see that you create a lot of scenarios, because we can create all of them maybe in the 3D.
And I have a question. When I tried to try different scenarios, I realized that maximum number of solar PVs are 5,000. And when I check the example, this diagram, I realized by, for example, the maximum number of solar panels that are equal to 5,000, the amount of consumed energy is highly more than produced energy. And I don't know how we can, what is the solution for that?
Actually, the essence of this workshop is based on these kind of questions, because in the website we get some sort of numbers, but these are not correlating with each other. So we will wrote the code for checking, cross-checking these numbers. So for example, when we put, I don't know, 300 photovoltaics in the scenarios, maybe for the calculations, we need 40 or 400 photovoltaics. So we make the calculation in the code and compare them, which number is the correct one. I'm not sure if I could explain myself clearly, but.
Yes, thank you.
So maybe I can see that you do not have any kind of problems for the code and the website. Maybe we can add photovoltaic numbers of these scenarios getting from the code as an additional information for the modeling part.
You mean the number of photovoltaic cells from that code that we tried in Google? I forget the name of it. Google Colab, or some other codes that you provide today?
No, we already provided that information in the Colab. So if you can open them, I think in the bottom part of it, there was total number of photovoltaic panels for the outcome.
I have to open the code.
It's
not, it's closed now, but okay. I will do that in a few minutes.
Maybe I can open them. Open it. I am opening right now.
I think I should stop my share screen.
Yeah. It will be better.
Okay.
So in the code, as you can see here, we can reach the maximum numbers of these, I don't know, habitats for the nitrogen levels, or maximum number of fertilizers, amount of fertilizers. At the end, for the storages, we add them up, but for that part, we can see that average energy consumption is some that number, and according to that number and some calculations that we made, we can reach the number of photovoltaic panels needed for this scenario. So for example, for this scenario, it was 118. But for example, for the other scenarios that you created, it would be, I don't know, maybe different kind of numbers. So we can calculate them while we are putting our scenarios in that code. I was trying to say that.
Yes, I got it. Thank you very much.
You're welcome.
Okay, so do you have any other questions, or we can proceed to the modeling part, the grasshopper part?
I have a question. It's not related to the topic, and it's about records of this session. Is it recorded today, and would it be possible to watch it in another day or no?
Yeah. The video is live streamed to YouTube. So we are live on YouTube, and after the session finishes, it will stay on YouTube. So you can always check the playlist. Maybe we can share the playlist link to the chat. So you can always go back and watch.
Okay, that's great. Thank you very much.
Welcome.
Actually, you can see the link from the useful links Word file in the drive. So you can reach them, the other videos and the today's and tomorrow videos from that link on YouTube.
All of the links of YouTube is provided in that Word in Google Drive. Yes.
Yep,
okay.
exactly. Hi, Mohammed, by the way. Welcome back. Would you like to share the CMOC results or Python codes? Do you have any trouble getting outputs or?
No, I didn't face much issues. I'm sorry for being late. I had a test at the uni. So
sorry, I couldn't hear that.
can you hear me?
Yep.
Yeah, I was saying I'm sorry about being late. I had a test at the university.
No problem. No worries.
Yeah, I tried it yesterday. I didn't have problems. I'll have to just run the code again.
Okay, great. If you have the outputs, we can proceed to the grasshopper part, because we will be using those Python code outputs as the inputs of the grasshopper, so that we have the generative system working. Okay, then I will start sharing. And like yesterday, we will go to this flow chart for the grasshopper part. and we will see the code in action. So you will see the actual geometrical result or architectural result of this flow after this session. So this, as you can see, this is a bit shorter or simpler version, because most of the things we handled in Python is about calculating the volumes so that we can proceed to the geometry. And using these data to produce geometry is handled like that. So I will make the brief version of this chart. So in the Grasshopper model, what we have done is this. We have some models for the Martian habitat, and these are clustered into three entities, and one is the habitat in which people can live, sleep, actually mostly spend their time in there. And the other one is greenhouse, mostly for the plants and the production, so that people have enough production, food supply to sustain their lives, and also for the oxygen, of course. And the third one is the storage, because storage is another important issue. And when we have these models, what we do is we provided you a simple parameter set in which you can select your model for each of them, for habitat, greenhouse, and storage. And there are three options for each. Okay, that's the first basic parameter that you will have in your Grasshopper code. And then other option is, these are not actually parameters, because we will be using the volume data that we have calculated from Python, but the other one is volume parameters, in which you can try different sizes and try to fit the calculated values in Python. By the way, I hope you can see as I'm writing the text. Okay, great. And the basic three operations to handle that is scaling the model so that it fits to the volumetric needs that we have calculated in the Python part. And the other option is to collecting model variations so that you can try different options and resolve a special layout clashes if there occurs any. But we have mostly handled that part, because the third option you will be using is the layout selection. And by layout selection, what I mean is that we will also discuss the advantages and disadvantages of them. The first layout is based on a linear architecture, where you have a linear connection path, and along this path you will have your units, for example, a habitat here, storage here, greenhouse here, the habitat here, and maybe another storage there. We will be using either this linear layout, and we will also have photovoltaic panels in front of it. And the other layout is the radial one, where you have your node and radial distances, and your unit will be like that. So they are distributed either radially or linearly. When you, for example, use a single node for the radial one, you will center a greenhouse, and all the other modules will be directly connected to the greenhouse, or you will have the linear layout and the greenhouse will be connected to the other modules indirectly. So there are some advantages and disadvantages. And also, since the modules can be changed, so you will have, for example, 3 different greenhouse modules. There are some differences between them, and we can also discuss them after that portion. And that's basically it. So the code works like that in its essence. And how the workflow appears is like that. So we had it calculated, the habitat volume, greenhouse volume, storage volume, and also the number of photovoltaics. I didn't integrate it into this workflow, but it's pretty easy. You'll see when you see the code live in action. And what we use is we have this model library for habitat, greenhouses, and storages. And as you can see, each of them will have 3 different options, and they will differ in terms of geometry, in terms of their structure, in terms of their volumes. And you're here as the user, and what we call this is the human in the loop. So you will control these 3 parameter sets, observe your results in terms of geometry, and also you will see the numerical results, and you will try different parameters, and you will try to fit those volumetric needs that we have calculated in the Python. So it's pretty easy, and how code handles it is also pretty easy. We will take our model library and we will select object with your input. So you will be free to choose any model you like, but of course you will be needing at least 1 habitat, at least 1 greenhouse, and at least 1 storage. But don't worry, code is handled in that way. So you will be selecting them pretty easily. And you will select your layout, and you will be facing 2 options. The first one is linear, as I said, like that, or the radial one, like this. You will either choose a linear one or radial one, but of course there are some different parameters. You can, for example, increase the number of nodes for the radial one, and you can provide some branching. So it's more like combined way of using linear and radial modules. And those are basically producing some lines or circles to distribute your module. And what the code does is simply divides the curve according to your needs. Actually, this should be also connected to here, because it divides and distributes your module so that there is no clash, there is no invalid architectural layout. And when you select your objects, of course, the habitats, greenhouse, and storage will not be using all of them, so it will be filtered. And what we have just calculated is the volume of each module that you have selected at the present state, and what is the volumetric needs of the actual simulation data. So we will be trying to fit this need and the actual result of our model. And the basic operation occurs here because we divided the volume of its actual model to the volume of the simulation result, and we get the square root of it, because if you want to control your volume, you need to use square root. Imagine it like that. If you want to scale a line that has the length of 2, and if you want to make it a line with a length of 5, you need to scale it with 5 divided by 2, right? But if you are in 2 dimensions, so if it's 3 by 3 square, the area is 9. But if it's 4 by 4, it's 16. So what you need to scale it with is 16 divided by 9, but square root of it. And similarly, if you are in 3D, in which the case is like that, in our habitat, you'll be needing the cube root of it, and we will use this data to control our volume, so that we will be sure that the volume fits to the needs of the simulation result. And basically we create vectors, first move the objects to their position, calculated according to the layout, and we scale the objects with this calculated data, and we calculate the volume back again, and we will see it in panel, volume 1, volume 2, and volume 3. And we will be, as designers, we will be the controllers of those parameters, and we will check the volumetric data of our generative model, the grasshopper code, and we will try to fit those volume data, the data that we have in Python as the output. So basically that's it. And there's another minor thing. We will use the photovoltaic panel numbers, number of needed photovoltaics, and we have a simple slider for that. We can control this slider and set the photovoltaic field to our model pretty easily, and then we will bake our results, take it into Rhino, and we will try different layouts and save them along with the data that we or the layout that we have tried in Simul. Right? Everything clear, or do you have any questions, any comments, anything?
I had a question. So, so we are trying to observe the results that we got after the Python. So we have those numbers, and then we by changing the parameters manually, we're trying to compare if we are getting the numbers that are similar, or are we running some optimization?
Good question. Great question.
Yeah.
Actually, we can use simple optimization methods at that point, like using Galapagos or any other optimization tool. But the thing about optimization tools is this. So I will clear that drawing if you're okay with that. So because I need more space. Okay. So the thing about the optimization approach is this. Imagine that you have a cube, simple cube. And imagine that you have 3 parameters: depth, height, and width. So you can control all these 3 parameters to obtain a volume, right? So if you use a single criteria optimization like Galapagos or Octopus or any other tool that you have in your hand, the optimization methods will have 2 problems. The first one is it can make a cube with 1,000 meter cube as the volume by setting width, depth, and height to 10, which will be a regular cube, or it can do it like that: 1,000 with width, depth as 1, height as 1. So we should control those 3 different parameters separately. It's my position in that, because we are making architectural decisions here in all these 3 parameters. But if you pass it to an optimization tool, it will make the architectural decisions not for you, but it will make the decisions disregarding you, let me say. So what we will use is simply taking the volumetric data, and we will use an approach in which that preserves the ratio. Okay, so if you have a habitat like that, it will not make something like this. So it will preserve the ratio. If the width divided by height is 1.2, it will be the same whether if it's at 10 meter cubes or 1,000 meter cubes. So we will not be using, we will not be in need of the optimization here. But what we'll use as an approach as human beings controlling parameters and seeing the output results, we will be the optimizers of this process. But of course, you are free to introduce Galapagos or any other optimization tool and observe your results. It's already almost ready for that, because we provided gene tools for parameters, so that you can shuffle it, you can use it in Galapagos pretty easily.
All right. Yeah, thank you.
You're welcome. By the way, the other problem about the optimization tools, mostly they dictate you a solution. They provide you a single prism, and they will say that that's the solution. But in this approach, you can try different parameters and see different layouts, see different geometric results, see different architectures, and you can choose among them, because the end results will pretty much the same in terms of volumetry, at least.
All right.
Great. Any other comments, discussions, anything? Okay, if not, we can give a short break and see the actual Grasshopper code along with the geometrical output. So make sure you have a Rhino and Grasshopper working. I will be showing the Rhino and Grasshopper with screen sharing, but after that we will pass the Grasshopper code to you, so that you can use and observe and generate your results. Okay.
Okay.
Great. Then I'm stopping my share. So see you in how many minutes? Do you have any suggestions to the break duration?
10 minutes.
Okay. Then
All right.
10 minutes.
Okay.
Great. Welcome back. Are you ready?
Yes.
Yes.
Great. I think I'm hearing myself. I don't know. Okay. Interesting. Hmm. Yeah, I think I remember. For that. A little technical issue. Okay, I'm sharing. We have resolved the issue. Yeah. I hope you can hear me.
Yes, yes, I can hear.
Great. So this is our Grasshopper code in action, and we will explore its parameters. This is an example layout. I will introduce you the basic things. This is a greenhouse. This is a storage. And these 6 little cute things are habitats. And how the code works, the first thing that you can control is either choosing linear or radial distribution of your models. And if you have chosen the linear one, in order not to confuse you, we will use these set of parameters for the linear one. These are all the things that you need to control. Not maybe all of them, but all of those panels will be used to optimize these 3 little yellow things. And this is the volume indicator of the habitat. This is the volume indicator of the greenhouse, and this is the volume indicator of the storage. And when you're using those parameters, you can control the number, okay? And this you can rely on that data. For example, this slider here is the number of habitats, which will be placed on this side. So if you reduce it to 4, for example, you will see that your number of habitats will be increased to 4. And how the gene pool works is like that. When you have 4 different habitats, this gene pool is used until here. So the first 4 numbers is the control parameters of the model selection. So the first one indicates this one, and the number 1 is the option, the model option for the habitat. So this one is option 1. The second one is 2 here, and this is option 2. This is option 0, which is here, and 2 again. So these 2 models are pretty much the same in terms of geometry, the layout. But what differs is the area, of course, and which will be controlled up to the first 4 numbers, since we have 4 different habitats. And the volume of the first habitat is 268. The second one is 248. This volume is 210. I'm following that. And the last one is 131. And as you can see, this is the total volume of your all habitats. And don't worry, we didn't cheat it. We didn't sum them up to calculate this. We actually take this data from the actual volume of those geometries and we sum them up. So it's not the representative way of validating it. It's actual way of validating our result. So let's observe how the parameters affect. For example, let's make 5 habitats, and if you change the first one, you will see that first habitat is changing in terms of geometry. You can either select 0, 1, or 2. And as you can see, as I'm changing, the geometry shifts a bit. The reason for that is since the first one is a bit wider than the third one, the second one, and we shifted the geometry in order to prevent some unintended flashes. So I can change those parameters, but code is written in a way to avoid some unintentional flashes. And this first parameter, actually the second, but the parameter number 1 is also controlling the second habitat. And this controls the third one. And as you can see, as I'm changing it, the volume stays the same because volume is controlled with those sliders here. And if I'm changing the fifth one, which is actually the sixth one, because I have 5 numbers in total here and 5 habitats, this will not change anything. But if you increase the number to 6, it will be functional, since you have the 6th habitat introduced into your geometry scene. And you can always play with those sliders to make the scale work for you. And don't worry, the minimum number is limited to 30, which is enough for a people to sustain their lives inside of it. So it's not, don't worry, this will not allow you to make smaller habitats that is impossible for a human to inhabit. But the upper limit is a bit large, so be aware of that and try to observe these volumetric changes so that it fits to the data that you have obtained from Python. Okay. It goes pretty much the same for the greenhouse. The approach is the same, and you can always increase the number. You can put 3 greenhouses, but make them, for example, smaller, so that maybe you can distribute the plants accordingly. So it could be an option. It could be the design strategy. And you can always use gene pools as right-clicking and randomizing them. If you don't want to try and control all of them manually, but try in a really rapid way to see how volume changes, you can, for example, try randomizing it, and when it comes closer to your needs, you can fine-tune them. For example, let's say that I'm needing 2,500 meter cubes of greenhouse. Of course, this will be the major parameter to control that. But if you will be needing 2,500, you can randomize and expect this value to get closer to your needs. And then when you get closer, you can always fine-tune them. And you can always double click. And no, actually don't double click it. I thought you will be able to double click and enter a specific number that fits for your needs, but seemingly it doesn't allow you. So you can play with that and obtain the volume that you have intended or you have needed. And same story goes for the storage. If you increase the number too much, you will see that architecturally it becomes weird, but don't worry, we will rely on the data, the actual simulation data. So it is not that easy to make it excessive, make it larger than it's intended, because simulation data adjusts and fits those well. But you have those freedom. And if you're using radial approach, the first thing you will control is the number of nodes. So if you, for example, increase it too much, this will not allow you to do and replace or place your modules, because what happens is this: if you have 2 nodes, each end node will have maximum of 3 branches. So you will be allowed to use 3 branches here and 3 branches here. And if you exceed these numbers, this will not allow you to construct, because if we have another branch here and another branch here, this will clash. So we prevent this in order to avoid some clashes. So if your model does not produce any nodes, be aware that you may be exceeding the number that you are intended to. And this is the number of nodes that you can control. And it's in each node, it automatically places a greenhouse. So this works as the parameter where you can control the number of greenhouses. And if you increase that enough, this will now allow you to build more modules branching from greenhouses. But beware of that. If you increase it too much, you will be losing space. Like this 5 nodes are actually be able to construct 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, and 3 more, 18 nodes, but you're only using 1, 2, 3, 4, 5, 6 of them. So beware of increasing your nodes too much, because you will be using an excess space and you will not be using it very efficiently. So try to keep that in a range that sustains your modules. And area adjustments are pretty much the same in terms of strategy. And when you're controlling them, you can observe that the branches are getting closer or diverging, because when it gets bigger, if you don't adjust your node to have enough space in between, this may lead some clashes or unintentional closeness. So it's also handled within the code. And these are for the storages. Now I have 2 of them. One is here. The other one is on the left side, I believe. Yeah. So this is another parameter, and both of them have photovoltaics. And how you can control photovoltaics is pretty much simple. Let's get close to that. Oh, too much. So if you can observe, the total number is controlled by 2 parameters. So total number of photovoltaics is indicated in that panel, and it's pretty easy to control. The first slider controls the vertical distribution, and the second one controls the in the other way. And if you play with them, you will see that numbers are arranged automatically. And on the yellow panel, you can read how many panels that you have in your habitat. And this one controls the degree. We didn't take the sun data, because CMOC is not using any sun data, and it's really hard to simulate how sun behaves in Mars. But of course, we can use some tools that we are using to control sun studies in the Earth, like Ladybug or any other tool like Climate Studio. We can always introduce such things, but since we don't have any scientific data for Mars, we don't use those data to control the angle and the alignment, but just for fun, we introduced the rotation so that you can play and set your panels rotations, so that it can be controlled. And I guess that's pretty much it. And all you need to visualize is controlled by this filter. And what this filter does, it takes the linear or radial data, and it takes all those data that you're controlling. It handles those calculations that I have mentioned in the flowchart, and it produces the geometry. What you just need to do, let's actually disregard the photovoltaics for now, because we can do them separately. What you need to do is to right click on those filter component and hit bake. You can select the group tick in order to ease your life. If you hit OK, you are safe to close the grasshopper because your data is already transferred into the Rhino. Then you have the model, the static model. All these parameters are really same in the parameters that you have set in Grasshopper. So you can save your model along with the data that you have used. For example, habitat 1 volume is 208. I don't know, habitat 2, 126, and like that. Greenhouse and is 400. So you can save also these data along with the model, and you can play with that. You can produce different results, and you can represent them all together, and we can discuss the advantages, disadvantages, and things like that. Any questions or anything that you want to discuss?
Yes, I have a question. So how does this relate to the data that we download from SIMOC, that website? I'm a little confused.
Actually, let's open up the CIMOC database. I hope you can still see. So everything starts with the CIMOC, and when you simulate with any configuration and any parameter, this produces the JSON data. Okay, and from here you can download your simulation data, and then, as you may remember, we go to the Colab code. We have passed this data to Python, and what we get is 4 simple parameters that are here, and this one. So what we need to fit in our generative model is already here. I see that total needed volume for the habitat is 1030. For the greenhouse, it's like nothing because I have chosen a layout that does not contain any plantation. And for the storage, it's 1121. And the number of photovoltaic panels is this. What I need to do is just, let's close this. If I have chosen the linear one, so right now my model contains, let's hide this. My model contains, and let's get it back to shape. Total number of habitats and total volume is 1,231. What I needed was, well, 1030, I guess. And what I will do is I will just select any model I like, because it doesn't affect the volume. But I need to adjust these values. Maybe I can decrease the total number to 5 and decrease the total volume of the port habitat a bit. Maybe it's too much. I'm decreasing this also. And voila, I have my volume aligned to the need of my habitat. So I can say that I have simulated a mission for, I don't know, 100 days in Mars with 4 people. No plant. Of course, I need to also adjust these. This is the greenhouse. So in the greenhouse, in the layout that I've tried, I didn't need any greenhouse, so I can set it to 0. So it will not build any greenhouse for me. And this was something like 1,200 and something. So I'm adjusting those values, and I have obtained the very same result that I've needed, and number of photovoltaics was 16. So I can make it 4 by 4 so that it will produce 16 photovoltaics in total. And I can say that, all right, for that scenario, for I don't know, 10 days, 6 people, no plant, and other parameters that you have used for the layout, I can say that this architectural model fits to this need of simulation according to the simulation data.
Okay, so can I understand as so the data from that website is usually provide context for our models here?
Yeah, actually, we have some assumptions like choosing a linear distribution or a radial distribution. We can say that we can always fit the volumetric needs, but maybe it can be resolved in a more compact way. But we have made some assumptions just to fit to the volumetric needs, because that's all the data that we have architecturally. Since we don't have the sun data, for example, we didn't introduce some rotations to the photovoltaics, or since we don't have the I don't know, the equipment that travels to Mars along with the crew members, and if they needed additional storage, we didn't have this data, so we didn't introduce into our architectural model.
Okay. Also, is it true? Is it as long as our values is bigger than the data that's needed, it's good to go?
Great question. Great question. The thing is, we should fit to the data at least to its minimum, but if you have done this, it would be excess. For example, let's say that your habitat needs 1,200 meter cubes for storage or habitat. But what you have built is 2,000 meter cube. So 800 meter cube is excess. It's too much, because since it's not easy and cheap, and it's not let's say as easy to build as in the Earth, we can say that 800 meter cube is too much, and it is built excessively, and it's actually unnecessary. But you can speculate. You can say that I sent 6 people to Mars, but my mission duration is too much. I don't know, 1 year. And you can say that I'm expecting 2 more people to be born on Mars, and you can say that 800 meter cube is for them for the future. But this will be like a speculation for a shorter period, for shorter missions like the CMOC simulation. What we need to achieve is a number as close to as much as close to that as possible. Okay.
Okay. Okay. Thank you.
You're welcome.
So do we have some sightings like 4 people and a garden, or no sightings? Oh, it's fun.
What do you mean by sighting?
Because I think there are many layouts, and yes, and with different settings there can be like hundreds of them. So in this workshop, do we have some basic settings like only 4 people, or there's no limit?
I see. For the Python, you can use the layout provided by CMOC and process this data, but for the Grasshopper part, we don't have any predefined settings. So we need to do it, but you can always randomize and try to expect this value to be fit to your needs.
Okay.
But it's a good idea. We can modify our code to have some predefined settings. So it will be
I think so.
Yeah.
And also, since it's optimization, so do we have some standards to see whether it's a good solution or a medium one? So do we have those standards?
Great idea. Great question. The thing is, we will discuss all together mostly tomorrow.
Okay.
We can
All
also
right.
discuss today. But for example, the volume is not the only thing. For example, if you have 4 people, there's no need to build 5 habitats. And even though you adjust the volume for the needs of 4 people, there are things like that. So you can always be careful about that, but we will discuss mostly tomorrow.
Great. Okay, thanks.
Great, you're welcome. Any other things before we proceed to playing around? So we will pass this Grasshopper code. We have already uploaded to Google Drive, so you can download. All the data that you need is internalized, so you can open it directly without any base Rhino file. It will be run automatically, so you can play around, you can bake, you can observe, you can play with them, and try to save as much as possible. Try to save different models, try to play with that, and try to correlate with your input, with the simulation data, with the layout, with the different settings. Okay.
I want to ask if there is a minimum volume requirement per habitat. Like,
yeah, actually, the minimum requirement is the real minimum for a habitat to for single person to live in is 15 meter cube for single person, but we have limited it to 30 because when it's 15, we have to build too many habitats, but we can we set it to 30 because it's more efficient. So instead of doing, for example, 8 different habitats for 8 people, we set it to 30 so that you can build 4 habitats and 2 people are living sharing the same space. So the minimum is scientifically 15, but in our model is 30.
all right, thank you. Yeah, got it.
You're welcome. Any other comments?
Actually, I have another, but it's in the previous. It's the logic part. So it's volume, but that chart it requires a square root. Actually, I'm a bit confused because volume is meter cube, right? But it's square root, so I didn't follow there.
Let me. Oh, sorry. I can release the. Yeah. Let's open Whimsical again. You're talking about this, right?
Yes.
So I'm taking the, actually it's not the square root, but the cube root. The logic comes like that. Imagine a line with a length of 4. The line is one-dimensional, right? And if you need to set its length to 8, what you need to scale is 2, right? If you scale it with 2, you'll be having a length of 8. But what about the square, 2D? 4 by 4 and 8 by 8. So if you, these are scaled by 2, right?
Yeah.
So this is the scale 2 version. Not scale 2 is not a breaking. A scaled by 2 version of this. But how the area changes? The area of this is 60, right?
Yeah.
We scaled it with 2, but area is multiplied by 4.
Yeah.
8 by 8 is 64, right?
Yes.
So 64 divided by 16 is 4, but we have scaled it with 2. What occurs is we scaled it with 2, but we have to square it to see the change in the area. And since we have the volumetric data here, the scale change is affected by scale factor over 3. So if we scale
Yes.
if we scale a cube with, I don't know, 2, the volume change is actually 2 to the power of 3. So it's 8. That's why we need the cube root. The mathematical formulation is like that. That's why we need cube root to capture the scale change, because we are dividing volume to the volume, right?
Oh, so this is the equation of oh, I see.
Yeah, this is just the Python way of writing this equation.
Okay.
So that's how you took cube root in Python.
Okay, I see. Thanks.
You're welcome. Anything else?
No, I think we can try it out.
Yeah, great.
That's really cool. Yeah.
Okay, then I'm stopping my screen share.
Well, while you are playing with the Grasshopper code, we are here for your questions. And we are expecting that if you could manage the code and the JSON file and the whole process, tomorrow maybe we can look at your baked models on Rhino. But we will be here for 30 minutes also. I will close my camera, but I can hear you. So if you have any kind of questions, we are here for you.
Okay, thanks.
Okay, thank you.
Can I ask a question?
Of course.
Yes, I have a question about the shape of habitats. And there are some, I think 3 or 4 shapes provided in the file. But if we want to shape some new form ourselves, how we should consider different factors. As an example, something that I've mentioned in the first session. I want to know if I myself want to design something new, how should I do that and consider which factors and how I can involve them in my design?
Actually, it's a very complex topic for our 4 days of workshop. So we provided that volumes for you for the Rhino. But for the overall concept, you can think of that you need to calculate, first of all, structural loads, which is mostly affected by actually the inner and outer pressures, because of the Mars atmosphere is not that much thin, that much thicker when we compare with the Earth. And after the consideration of these structural loads, we can think of our storage needs. So with that knowledge, we can produce our forms with that knowledge. So, for example, for these volumes, you can see some sort of literatures about these issues in the Drive folder. I think I added them yesterday. And also in the useful links, you can see structure challenge for space architecture link. And in there, they explain it in a very clear and they summarize the issue actually. So if we want to create this sort of volumes, we can use the structural and also mechanical considerations. And beside them, we need to think about the material. So when we consider and when we decide our structural volume, for example, we can use inflatable or deployable structures. When we choose one of them, for example, we can create our design according to that. I'm not sure if I could explain clearly.
Yes, but as you mentioned, the time of workshop is limited, but I want to know if I want to know more. I saw that PDFs that you provided in Google Drive, but is there some another maybe I don't know, applications or softwares or something like that that we can use them in order to calculate something that we need in our design or something like that? And
yeah, I'm sorry, I interrupted you. Please continue.
I have another question that you said we have 2 types of structures, inflatable and deployable. These are 2, we only have these 2 types, or no, it's a really greater amount of types?
Actually, we can create any kind of structures if we calculate our structural load and the other kind of loads for the Mars. But for the first question, right now we do not have that much comprehensive simulations or any kind of programs, softwares for that issue. But with adding some these knowledge together, it can be in the future. But for the structural types of these issues, we can, it's not the only options. So, for example, we can create 3D printing sort of structures that it's actually done in Earth also. So that's these two of them was the first things that come in my mind.
Thank you. And another questions that for an example for these shapes or another shapes that the structure looks should be estimated in rhino and grasshopper or no? They have done in some other applications or no? With some plugins, we can do that in grasshopper.
Actually, with the finite elements methods, we can create these sort of calculations in Grasshopper also. But for example, for the civil engineering part of it, they were using, if I'm not saying it, I think so, yes, they were using MATLAB and also SAP, I believe. I'm not sure, but they are using these simulation tools, and actually there is no database about it, so they were estimating it.
Thank you. I think I missed first part of your speaking that you said. I realized MATLAB and SAP. I think you mentioned some other thing that maybe Rhino, or unfortunately I missed that part.
And they were using finite element methods in Grasshopper with some sort of plugins. So with that method, they are estimating these sort of loads.
Thank you. Would it be possible to write the name of, because I didn't understand clearly. Thank you very much.
You're welcome.
And another question about the degree of photovoltaic panels that was 15 for maximum. Is that something that's calculated based on the sun radiation, or no? It's just something that provided in the grasshopper.
Actually, I'm sorry, I interrupt again. Please.
No, I finished my speak.
Okay. Actually, it is related with the panel's power about this issue. So, for example, I will share my screen to show the explanation about it in CMOC. So I'm opening it. I hope you can see my screen right now. For example, in here, when you click on that eye icon, you can see some sort of explanations about it. Most of the photovoltaic panels has different kind of power actually, but for these simulations, actually not for these simulations, for this model, we standardize it, and actually for the 2 square meter of the panel in Earth, for example, we can create that much of energy for from the sun, but in Mars we are not getting that much light as we in Earth, so the panel power reduced by 30%. So if you can look at the, I will open it. Code. In the code, we are multiplying a number, which is that number that we are reducing it. So we are reaching that number with these calculations. Yes, for example, that number. We are trying to reach that average energy consumption value in kilowatt hour with multiplying that numbers.
And thank you. That was about the amount of that. But my question was about the degree of solar panels. I want to know if the optimum degree is between 0 and 15, or no, that's just some number that's provided in the grasshopper.
Actually, it's some numbers provided in the grasshopper, because I will stop my sharing, because we need to understand how the azimuth of the sun light coming into that direction. Because, for example, when we think about the photovoltaic panels, you can think it's my hand is a photovoltaic panel. The maximum output can be provided with the 90 degree of the sunlight. So if we are sure about it, we are sure in Earth, but we are not sure right now in Mars. There's a lot of calculations in there, so we didn't add it in here, not to confuse for that issue. So the degree is related with the coming sunlight, with the 90 degree for the panels.
Thank you. So our knowledge about the azimuth in the Mars is limited at that moment.
Yeah, actually, there is some sort of information provided by NASA with the Curiosity rover and the other rovers getting information from Mars. But we are not sure right now where we locate these habitations on Mars. So because of that, we couldn't put that information in the grasshopper. It's changing according to location.
Yes, thank you very much for your information.
You're welcome.
I have a question. So I noticed that different space with different functions has different shapes. And just out of curiosity, are these shapes designed for some kind of purpose or just to be convenient?
Actually, it was chosen with the approximate approach about this issue, because, for example, the rounded shapes are very convenient for the Mars because of the, as I said earlier, the loads, and also the, I don't know, the sun storms and the other kind of issues for the Mars issue, Mars concept. So there were some sort of conceptual approaches, but they, if you could examine the literature folder in the drive, there is different kind of approaches about this issue. For example, I am opening some of them in order to remember the name. Yes, there were Mobitat 2. So it is an mobile habitat. So it has some sort of triangulations, and it's very much likely with that one. I will share with you.
Okay.
Yes. For example, it's very much like that one, but for the rounded ones, it's very similar with these shapes. So this kind of approaches we use that.
Okay, thanks.
So is there any more questions about the subject?
No, thank you very much for your information.
Of course. And also you can look at their references. There's a lot of valuable information in that reference also with these PDF files.
Yes, I will check them. Thank you very much. And if it's okay,
Yes.
I leave the session because I should attend another mission at that moment.
Okay.
Thank you very much.
You're
See you
welcome.
tomorrow.
So if there isn't any question, we can also wrap it up and
I have
yeah, okay.
a smallish. Okay, I'll just quickly share my screen. Is my screen visible?
Yes.
Yeah. So based on the data that I got, I took the same setting for humans and garden, but I think the volume is slightly high, and when I'm trying to build, let's say if I go to linear, I cannot. So it's 300 is the max. So if there are 4 habitants, maximum we can hit is like 1200. So then to reach this, we might have to like go for even more, like 8. Like is that okay? Like having 8 units, but for 4 people.
Yeah, and actually it's a bit unbalanced in terms of the habitat number and the volume aligned with the greenhouse and the storage. Maybe for that case, the radial can work better because it will allow you to make more branches. And since you have the greenhouse, maybe you can split the greenhouse volume into 2 so that you will have 2 nodes which allows you to have 6 different nodes, but you can also make it. What was the volume of the greenhouse according to the
Greenhouse is 441 or 41
441?
Yeah.
Okay,
Yeah.
it's a bit less. Yeah, you are right. It's quite unbalanced scenario. Maybe you can go back to your simulation settings and maybe increase the plantation a bit so that greenhouse grows, and then you can choose the radial option to make 3 nodes with 3 greenhouses, smaller ones, and you will have enough nodes to accommodate 8 people or 8 different habitats.
Okay. One. What was the node option?
The at the very top on the leftmost corner. Yeah, the little box here. Can you go to the very top? I will annotate its place.
The very top.
Number of nodes, right? You're asking. Yeah. Sorry. I thought that it's the radial thing. So below here, the slider controls this slider controls the
Okay.
number
This
of nodes.
is the nodes. Okay.
Yeah, you have 3 nodes, so you can arrange your greenhouses according. But that this may happen. So the problem is related with the balance between resources when you first set the simulation preset.
Okay.
But you can always save the unbalanced version so that you have different options, and we can discuss together tomorrow.
Okay. Yes, I'll try it out. Okay.
Yep. Great.
Okay. Thank you. Thank you so much.
So maybe we can ask from you that you could, if you have time, you could be able to bake various number of scenarios. It will be better to discuss about these issues for the tomorrow's session. And if you do not have any questions, maybe we can close this meeting.
Okay.
Okay. See you tomorrow then.
Yeah. Bye. Bye. Bye.
Bye bye.
You.